So today we're going to start with a concept, a math problem. And you may have noticed there were things that we were doing before today where we were looking at Boyle's law. And today what we're going to do is learn how mathematically to work with Boyle's law. So, many of you that have been keeping up with the work online answered questions about Boyle's law, and you did the FET on Boyle's law. And I'm going to illustrate this slightly differently. You might remember a long time ago we did, or maybe we did a FET called States of Matter, and you can always look that up independently. But the idea behind it is, let's say I've got a finger here. It's going to be a long finger. And it'll be attached to a wrist. How do you do that? Yeah, you got a little bump there. And then it goes up into the fist. And you got a thumb somewhere. And then there's an arm. Maybe that's not the best finger in the world, but I don't judge, right? So here we've got a container, and inside of it we're going to place a gas. And as you can imagine, the more of these particles I put into this space, the greater the pressure is going to be. And the more I push down on this space, the closer these particles get compressed together, and they're going to decrease in volume. And really that's what Boyle's law is about. It's looking at just volume and pressure. Over the coming days, we're going to look at several other of the gas laws and what it is that you can solve with knowing of them. So first, we need to clarify some of our lingo that we're going to be using here. If we're looking at volume and pressure, we better know what our units for volume and pressure are. So I'm going to make here a little box, and I'm going to label it volume units. And there are many volume units across the planet Earth. Just like, you know, there's different currencies and different languages. However, as far as we're concerned, the only volume units we're going to work with, at least as far as I know, are liters and milliliters and centimeters cubed and meters cubed. So these are all units of volume, and we'll be looking for these in our problems. And our other variable that we'll be working with is pressure. So we'll need some pressure units that we will become familiar with. Now, with pressure, there's a lot. Some of them you might be familiar with, like if you've ever filled your tires on your bike, or if you're old enough to have a car, is something called PSI. That's parts per square inch. That's a unit of pressure. And in weather measurements for the atmospheric pressure, a lot of the times there's another unit of measurement called millimeters of mercury, because old barometers used mercury for measuring pressure of the atmosphere. We're not really going to use those because they're not going to fit into our science-y stuff that we're doing here. What we're going to do instead is use these pressure units. There is one pressure unit that is called the ATM, and that stands for atmospheres. And ATM is 1, this is kind of helpful, is 1 at sea level. So throughout the earth, I guess if you're at sea level, the atmosphere will be equal to 1. So our atmospheres here in the North State are at sea level, or it should be 1. Okay, now our other pressure unit that we're going to need to know is the kilopascal, which is written with a capital K and a lowercase pa. And that's the dog. A kilopascal. And so these are the two we'll be mostly working with. These I just put so that you could make some reference to something you know about out there in the world. So Boyle's law is simple. Because we're dealing with pressure and volume, and like you saw in the videos, we're going to have pressure, and we're going to give it a time frame. So we're going to have pressure 1 and pressure 2. Pressure 1 is going to represent the pressure before we did something to it, and pressure 2 is going to identify the pressure after we did something. So we have pressure 1 and volume 1 is equal to pressure 2 and volume 2. And I'm putting these little dots in to represent multiplication. So pressure and volume in the first set of conditions is going to be equal to the pressure and volume in the second set of conditions. So looking here, this would be my first set of conditions. I have a certain amount of pressure, I have a certain amount of volume, and when I push down on this, my pressure and my volume are going to change and become pressure 2 and volume 2 after the change, whatever that change is. So what I want to do is have you open up your worksheet that I've attached, and you don't have to print it at all. All you have to do is to be able to view it. And I want to take a second to look and see how they've organized this. So these are all Boyle's law, I think from 1 to 4. And so we can draw a line here. And these have marks on it from previous years. But here we've got pressure 1, volume 1, pressure 2, volume 2. And you'll see these units of pressure and units of volume. One of the things you need to make sure is that your volume and pressure units are the same for both parts of the problem. For instance, here on 1A, I have kilopascals here, and I need to check and make sure I have kilopascals here. And here I can see I've got centimeters cubed. I need to make sure I've got centimeters cubed over here. And I guess there's some potential that they wouldn't be the same in a problem. Maybe not necessarily in these problems, but in the future. So beware. They need to match. All right, so we've got P1, V1, P2, V2. And the thing we're missing is this P2. So what we need to do is rearrange this equation to solve for P2. And in order to do that, we need to have this one isolated on one side of the equal sign, and everything else needs to move over to the other side. So how are we going to do that? I think I'm just going to drop it down with the equal sign. I'm going to leave these guys alone because they're perfectly fine on their side of the equation. So I'll have P1 times V1. And then this V2 here, if I move this over to this side, I'm going to need to move it down into the denominator. Remember, nominator is what you call the region on top of the fraction, and the denominator is what's on the bottom. So if I take out my calculator, oh well, first I need to plug in some numbers, but if I do that, then I should be able to solve for the answer. So let's try it. I've got here on my handout that you can be just looking at on your computer screen is P1. P1 is 127.3. So I'm going to put the 127.3 right here, and I'm going to multiply that by V1. Whoops, that's dumb. I should have put my kilopascals in there. K-pa. I like to call them K-pas. I don't know. That's not accurate, but it's fun to say. So we've got, that is multiplied by V1, which in this case is 796 centimeters cubed. And then all of that will be divided by V2. And V2 in this case, we can see is 965 centimeters cubed. So these units will cancel, leaving us with a kilopascal for our P2. So let's do that. P2 is equal to, we're going to have to pull out our calculators. And we'll take 127.3 and 796. And we're going to divide that by 965. 965 divided by. Okay, once I do that, I get a number here. And I need to ask myself about significant digits. And so when I look here at this problem, provided I wrote everything down correctly, how many significant digits should my answer have? Right, it should have 3 significant digits. So I have, I don't know if you can see that okay, but I have 1.05 times 10 to the 2 kilopascals. And that's it. I'm done. So you can see that's pretty darn easy. For some of you, you might find that the more difficult part in this set of problems is the rearranging of the equation. Yeah. So to help you out with that, I just want to remind you that whenever you move something across the equal sign in an equation, you have to divide or multiply each side of the equation by its reciprocal. So in general, when I moved this V2 here, what I really was doing, I just moved it because I know I can. But ultimately what I'm doing is I'm multiplying each side of the equation by 1 over V2. And for you folks that are good at rearranging equations, I don't want to confuse you with all that, so just skip all that. But, you know, this is what you, in essence, are doing in order to isolate this P2. Okay, so let's move on and try B. I'm overly optimistic I can fit it all into this section here. When I look at B, I see that V1 is the variable that I'm missing. So I start with my P1 times V1 equals P2 times V2. And now what I need to move is my V1. So I'm isolating, oh no, not what I need to move. What I need to isolate is my V1. So I need to move this P1 over here. So I'm going to leave that V1 right where it's at, and I'm going to write the P2 times V2 right where it's at, leaving it alone because I don't need to move it. But this P1 does need to move. And so I'm going to move it here to the bottom because that's where it needs to go. And now I'm ready to plug in my numbers and solve. So if I go back to P2, I've got 9.6 times 10 to the negative 1 ATM. And my V2 is 3.7 times 10 to the 3 milliliters. And all that will be divided by P1, which was 7.1 times 10 to the 2 ATM. Okay, so those will cancel, leaving me with milliliters. And I think I'll write my answer right here just because that's where the room is going to be. And so that will be V1 is equal to, here we go, 9.6 times 10 to the negative 1, 3.7 times 10 to the 3, and all of that is going to be divided by 7.1 times 10 to the 2. And so I get, looking here at my significant digits, I should have 2 significant digits. So I'll have 5.0, and that's going to be milliliters. It's a nice even number. Okay, so what I want you to do for me is to finish through F. So that's do 1, I'm always doing that, to 1A through 1F. And I'll give you the answers tomorrow so you can check them and see what you did wrong, what you did right. Okay, that's it for today.